All right, we're going to finish up this lesson because it turns out I talk a lot, and we just covered a whole bunch of concepts with number 1 and number 2. I guess that's the point of what I'm doing. So now we're going to jump into number 3 and number 4 and cover in a whole bunch of other concepts. And for some reason, when I look at number 3 and number 4, the Kenny Rogers song, "The Gambler," comes into my head because you got to know when to hold them and know when to fold them. It's all about awareness. It's the awareness that I talked about in the previous lesson for multiplying. It's all about being aware of when you use things and when you don't use things. Okay, we're going to hit 2 ginormous concepts with this one question. We're going to hit 2 very, very big concepts with this one question. Now, the first thing you can do is look at this problem and think, well, based off of what Katz did the other day with number 2, can't we apply that principle in the numerator and then apply that principle in the denominator and see if something cool would happen? And the answer is yes. Yes, you actually could. But there is also another way to do this as well. Okay, so there's actually 2 ways to approach this. I'm going to cover 2 concepts. The first is this. You have to remember this. The square root of a over the square root of b is actually equal to the square root of a over b and vice versa. Okay, so this little thing can work backwards or forwards. And sometimes you can use it and sometimes you don't have to, right? So sometimes you can, sometimes you can't. And it's really a matter of personal choice and what you're looking at and what you might think will occur. So I guess what I'll do is do number 3 2 different ways just to demonstrate this. So you might think again, let me simplify the numerator and then let me simplify the denominator and go from there. And that's possible. It is possible, and I'll show you how. But let me see if you can be aware. You got to know when to use this and know when not to. Okay, so that's why I go to Kenny Rogers song. I'm gonna use this principle now. Okay, I'm not gonna not use it. I'm going to use it now. So what this means is I'm going to take this crazy radical fraction and put it all underneath. And if I have a problem set up here, I'm going to see if I can do stuff with it. Now, sometimes, you might run into a problem that looks like this, and you may be asked to simplify it. And you might want to go back the other way, right? You can take this, split it up, and do some crazy things, and you might want to do that. Or sometimes you can work within there. So it's all a matter of awareness. So be aware, come up with a game plan, okay? Awareness. At this point, when you're looking at fractions, come up with a game plan. What's your plan, man? What do you think is going to happen? Now, your game plan could be one of 2 things. You could either simplify what's inside, or you can split it up. If I knew how to spell split. There you go. Split it up. So you can come up with a game plan, right? And that's your awareness. You want to simplify this, or do you want to split it up into that? And it's really, it doesn't matter. I mean, the reality is that you should get to the same result no matter what. When I'm looking at this particular expression, my game plan is going to be to simplify it. I'm going to choose this, and the reason why is that I am aware of the numbers 20 and 45. I am aware that they have a common factor of 5. And I'm also aware that if I simplify 20 over 45, I'm going to end up with 4 over 9. And that's a handy number to work with since we're dealing with square roots. Okay, so I have to be aware of all of these things, and that's why I'm going to simplify. So let's go ahead and simplify what's inside, because I am aware that when I simplify this, I'm going to end up with 4 over 9, which is a handy number for a square root. So I know 20 over 45, like I said, both can be divisible by 5. You end up with 4 over 9. But if I'm going to simplify that, I may as well simplify my a's and my b's. I know that the a's will cancel to leave me 1 on the bottom, and the b's will cancel to leave me b squared on the bottom. So I know from simplifying, my particular game plan is going to end up with the square root of 4 over 9ab squared. Okay, I'm very aware of that. I'm very aware of that. Okay, so now I have simplified this, and this is this ain't cool, by the way, because one of the definitions of a rational number, where you have a number that can be expressed in terms of a over b, where a and b are integers, b has to be an integer. We cannot have an irrational number in a denominator. Okay, and then when you get to trigonometry and start dividing by pi, feel free to ask that question because that's awesome. All right, so we can't have an irrational number in the denominator. So what we have to do then is split this back up. Okay, so denominators must be rational. Must be rational, must be integers as well. Okay, so it must be rational and must be integers. So I should probably have, let me cross it out. Denominator must be integers. And the reason why is just the whole concept of division, splitting up into a certain number of equal parts. But anyhow, denominators must be integers. How are we going to work with that? That's crazy. So we have a denominator that's inside a radical. So what do? We go back to this rule. We're going to employ it again. Okay, so we've already simplified. Now it's time to split it up. So we have this. Now we can split it up because I'm telling you that 4 over 9 is a handy deal. So I'm going to split this back up again. And then I have the square root of 4 over the square root of 9 times ab squared. And then I can start simplifying the denominator. We're going to get into another crazy thing in a second. Okay, so the square root of 4 is 2. Again, we're dealing with principal roots. The square root of 9 is 3. Okay, again, dealing with principal roots. And the square root of b squared is b. Again, dealing with principal roots. And then we'll be left with the square root of a. All right? Now, craziness is about to ensue. All right, so first of all, we do need absolute values for the b. But that's not the point. The point is, what in the world do we do with that square root of a? Denominators must be integers. That's a big no-no. No radicals in the denominator. That's a huge rule. So we're screaming, no radicals in the denominator. So what does that mean we have to do? We have to do something called rationalizing the denominator. We've done this before with imaginary numbers. So we got to remember, rationalize the denominator. Come up with a clever one. Okay, remember that? A clever one that will result in the denominator being cool. That will leave a, I'll call it kosher, fit a kosher denominator. Okay, so a clever one that will leave a kosher denominator, a denominator that is okay to be allowed, because we can't have radicals in the denominator. So here's the question. This is where things get nuts. I have the square root of a in the denominator. How in the world can I get rid of the square root of a? So let's do a couple of examples. Okay, let's go over a couple of examples, and then we'll be able to finish that problem. Let's say I have 1 over the square root of x. What in the world can I multiply by the square root of x that would give me a kosher denominator? Well, since we're dealing with the square root of x, right? The square root of x, if I just multiplied it by the square root of x, wouldn't I get x in the denominator? Right? Isn't that how that works? Isn't the square root of x times the square root of x just x? That's thinking, right? We totally have to think. And if I multiply the denominator by x, I have to multiply the numerator by x, thus the clever one. Okay, so here is our clever one. That was clever. Okay, so if I had the square root of x and square root of x, it gives me x. Everything's taken care of, just the same way we did with imaginary numbers, okay? But now I have to fix the numerator. 1 times the square root of x is the square root of x. And that's that's kosher, right? Don't call that 1. You can't cancel this. This certainly is not x. This is the square root of x. We can't cancel that. This is as good as we can get. Now, let me do another example, because I'm going to unlock like a big piece of thinking in your head. What if I had 1 over the cubed root of x. This is where stuff gets nuts. Okay, now remember, no radicals in the denominator. That's totally illegal. What do we do? Okay, so what do? We have to think of something I can multiply by the cubed root of x that would get rid of the radical. Now we have to remember, like another think, did you know the cubed root of x cubed is x? Right, so you got to remember that. The cubed root of x cubed is x. So what could I multiply this by? What would be the clever one that I could multiply this by that would give me an x out here, right? That's basically the thought. What in the world can I multiply this by that give me x in the denominator? Well, I have to make this the cubed root of x cubed. That means I'd have to multiply by the cubed root of x squared. And you have to be careful. You've got to totally be careful. The index stays the same. The index stays the same. And just like in the last lesson, this is as simple as we can get. So my clever one is actually going to be the cubed root of x squared over the cubed root of x squared. That's my clever one. And then when I multiply the tops, of course, I get the cubed root of x squared over x. And you can't simplify that. This isn't x. This is the cubed root of x squared. Totally not x. The cubed root of x to the third, that's x. This is not x. This is x. Not x, x. All right, one more example just to keep your brain turned on. Brain turned on. Activate. 1 over the cubed root of x squared. Okay, so how would I rationalize that denominator? Okay, what is the clever one I would have to multiply by to get me freed up? Clearly, the cubed root of x. Right? If I multiply this by the cubed root of x, would I not get the cubed root of x cubed, thus resulting in that? And that's where things get fun. Okay, so there's my clever one, and then I'm left with my numerator, and that's just how that works. All right, that's all about rationalizing the denominator. Okay, so that's the whole concept of rationalizing the denominator, which brings us back to where we left off in our problem number 3. Darn it, we have a radical in the denominator. So we must think of the clever one. We must think of the clever one that we could multiply this fraction by that would get rid of the radical. All right? So did you happen to know that the square root of a times the square root of a is equal to a? If you remember that, that's going to make life easier. And there is your clever one. So if I multiplied the bottom by the square root of a, that would multiply itself out and just become good old a. And then I'd have 3ab in the denominator. Okay, so I would know this. Actually, both would be in absolute value. So I have 3ab in the denominator, right? Square root of a, even index, odd exponent, absolute value. But I have to multiply by a clever 1. So how's that going to impact the numerator? Okay, so if I'm multiplying by a clever 1, that's the situation here. I have 2 root a in the numerator. So I'd have 2 root a times over 3ab, ab in absolute value. Whoa, whoa, that's crazy. And that's how we attack number 3. So let's go back, right? So we say, here's number 3 that was the original. We had to do, know when to hold them, know when to fold them. We're going to simplify first, and then we'll split it up, and then we rationalize the denominator. And as I mentioned, there's another way to do this. So let's go ahead and do it the other way. So we're going to do number 3 all over again, but this time another way. So we have 20ab over the square root of 45, a squared b cubed, and we can simplify the numerator. 20ab. If we're going to simplify the numerator, isn't 20 4 times 5? Isn't the square root of 4 2? So this would give us 2 times the square root of 5ab. All over this, okay? Isn't 45 9 times 5? And isn't the square root of 9 3? Okay, and now inside the radical we'd have 5. And isn't the square root of a squared a? And isn't the square root of b cubed b? b squared times b, right? So that would leave us 3ab times 5 root b, okay? So that's the setup so far. And now remember, we cannot have a radical sign in the denominator. So what could we do? We could do a couple of things, which is kind of cool. So let me show you this way. Remember the rule, the square root of a over the square root of b is square root of a over b. I'm going to employ that rule right here. So check this out. I have 2 over 3ab, and I'm going to multiply that times one big square root. 5 times ab over 5b. I'm going to know when to hold them, know when to fold them. And now this time I'm going to take that rule and go back the other way. Now I can simplify what's inside here. Check this out. Bloop, blamp. And what am I left with? 2 times the square root of a in the numerator over 3 times the absolute value of ab in the denominator. Okay, so either way, we are all set on number 3. Okay, and that's dividing radicals and rationalizing the denominator. And that will hopefully make number 4 a whole lot easier. I hope that was cool. To me, that was neat. I can do it either way. All right, on to number 4. We're going to simplify this. And the good thing is I already covered the basics. Okay, so we have now, number 4, the cube root of 5 over 3 xy squared. Now remember, the whole thing with employing this rule, all depends on being aware. Do we want to simplify or split? So we're going to come up with a game plan. Simplify versus split. Since we can't simplify anything here, we're going to have to split it. Okay, we're just going to have to. We have to. So in the numerator, we have the cube root of 5. In the denominator, we have the cube root of 3xy squared. And this is where the thinking cap's got to be on. Now remember, how do we rationalize the denominator? If we're dealing with the cube roots, right? We have to remember, note that the cube root of x cubed is what will get rid of the radical sign. The cube root of x cubed gets rid of the radical sign. So, how do we get rid of the radical sign for this 3? There's only one 3 here. How many more 3's would we need to multiply in order to get rid of it? Okay, so we have to start thinking. We know we're dealing with the cube root of something. We consider the 3, okay? There's only one 3. We need 2 more 3's in order for it to cancel. So we're going to multiply the 3 times 3 squared. And if you can see what's going to happen, we're thinking, we're being aware, that would be 3 cubed, thus freeing the 3. Not freeing, I don't like that term, but anyway. Here's an x. How many more x's do we need to come to here? 2 more. Here's a y squared. How many more y's do we need to satisfy this? 1 more. Okay? So if we're multiplying the bottom by that, we're multiplying the denominator by that, that's what's going to free up the denominator. Okay, so the cube root of 3 times the cube root of 3 squared is 3. The cube root of x cubed is x, and the cube root of y cubed is y. So by picking this clever one, we can have a kosher denominator. But remember, we're dealing with a clever 1. So we have to multiply the numerator by the cube root as well. So we can call that 9. X squared y. And if we're going to multiply that in the numerator, well, we multiply what's already there. We have the cube root of 5 times the cube root of 9x squared y. Don't be a noob and leave that, right? Don't leave that because that's noobish. We can put these under the same radical sign. So that we can simplify even further. 9 times 5 is 45, x squared y, and that is all over 3xy. And that is that's a kosher rational expression, radical expression, because we don't have a radical sign in the denominator. Okay, so we have to do a lot of thinking, and the practice and the homework will really help a bunch. So hopefully that helps, with dividing radicals and Practice, practice. Thank you.